Donna Moshkovitz will tell us about mixing and lower bounds for space-bounded memory.
Thanks, Andre. Hi. Okay, so I'm actually going to talk about paper that is the intersection of the two programs that are running right now at the Institute. One is the Pseudorandomness program, and the other is the machine learning program. So this is about this new line of research a lot of work in the past year or so, year to year and a half, on space-bounded learning. What happens to learning, to just normal PAC learning, where when you restrict the space that the algorithm can use. And we give general results that give low bounds whenever the hypothesis class is pseudo-random in a natural way. So this is what this talk is about. This is joint work with my sister, Michal, who's a graduate student at the Hebrew University. She's part of the neuroscience program there. She does machine learning, but originally she's actually a theoretical computer scientist. And this whole project started because she heard about this kind of machine learning problem that had this fun theory flavor, and she thought that this is a puzzle she could solve. Okay, so I'm going to give kind of a weird talk in the sense that I'm going to talk about confusion, about low bounds. It's about how, if you can't remember everything, you're a learner and you can't remember everything, and you don't have endless time, then you're basically screwed. It's very easy to confuse you. I'll try to give a non-confusing talk about confusion. Okay. Okay, so let's talk about learning. So here is the basic fact. Suppose that I have some hypothesis class. So I have X is a set of examples, and I have a hypothesis. Each hypothesis is a function that gives for every element in X either 0 or 1, labels it either with 0 or with 1. And what happens is that someone picks some hypothesis, and now we keep seeing examples that are consistent with the hypothesis. Okay, so we see various X's drawn from some distribution, and we see them labeled with the evaluation of the hypothesis on them. Okay? And kind of a standard definition of PAC learning says, you want for every hypothesis, no matter what's the underlying hypothesis, no matter what the distribution you get over examples, with high probability, the learner will come up with some approximation to the underlying hypothesis that is very good with respect to the distribution. Okay. And the fact is that it's always possible to learn after seeing only a logarithmic number of hypotheses. For many classes, you can actually do much better. But this is always true, and roughly it's because if you see random examples, they roughly mostly cut in half the space of possible hypotheses. So after log H examples, you're good. Yeah?
What the probability H prime is not equal to H be less than 0.01?
What? Okay,
the probability of H prime not equal to H.
Yeah. Yes, no, not equal. Yes. Yes, thank you. Yeah.
Well, when you say one can learn, do you mean that there's actually an efficient algorithm to do so, or just an algorithm that would work that's not necessarily?
There is an efficient algorithm. Just get those examples and just see what's consistent with that. Okay. But here is the relevant point if we care about memory. Implementing this algorithm actually requires remembering all those log H examples that you got. Okay? So the number of memory states you need is X to the order log H, which is kind of a lot. It's also H log X, also 2 to the log H log X, and it could be a lot. Okay. Now the question is, can we also learn with fewer memory states? And we can by brute force learner. So here is, so the first observation is that if we want to uniquely identify the hypothesis at the end, we need to have age memory states. Okay. Now, Park learning doesn't say that you have to identify in the end. Maybe you do if all the hypotheses are kind of far from each other. So an approximation basically means that you also figure out what's the hypothesis. Maybe you can save a little, but age is kind of the ballpark for the minimum number of memory states you would need. And it turns out that you can actually learn with this number of memory states. And here's the algorithm. I'm going to enumerate each and every hypothesis I have. I'll start with the first, and I'll say, OK, I think it's a first. Let's start seeing examples until I see something that is inconsistent with that. OK. And then, OK, no, I saw something inconsistent, so let me move on to the second hypothesis. Let me wait until I see something inconsistent with that, and so on and so on. And in the end, I will find out the right hypothesis. So I only need to remember what's my current conjecture. So that's age memory state. And after age log age examples, I should know what's going on.
What kind of access to the examples do you assume? I can sample at any point in time and get a fresh random?
I get random examples. I get examples labeled with what's age of these. Okay. Now, so let's plot what we know. We have those two axes, how many memory states we have, and how many examples we have. And we saw two algorithms. The first is this, not the first, one of them was a brute force algorithm. So it has very few memory states, just age, which is great, but huge number of examples. And we saw another algorithm, which is just the standard path learner, that uses many memory states, much more than age, but has this great memory usage. And kind of the question is, OK, can we get something in the middle, meet in the middle? Maybe can we improve things so we use maybe a bit more than age memory states, a bit more than log age examples, but get a good algorithm. And this would be great. Okay, so this is the question. Pictorially, the question was raised, actually, as far as we know, by two independent groups. One was Ohad Shamir from the Weizmann Institute, and the other is a group from Stanford, Greg Valiant and Steinhardt and Wager. And they asked, suppose that you want to learn with less than what the Park learner needs, substantially less, what can you do? How many examples do you need? Specifically, do you have a question? No. Specifically, the second work actually suggested the special case of parities. You get like something like x1, XOR x2, XOR x3, XOR x4, and so on, but you don't know what are the variables involved in the XOR. Now learn just from seeing examples. And indeed, some time after this paper appeared, Ran Raz found a way to prove very strong low bounds for learning parities with n variables. Parities with n variables, so you have the number of examples is 2 to the n, 0, 1 to the n. And the number of hypotheses, right, is any choice of one of the a subset of the n possible variables to put in the parity. So age and x are both 2 to the n. And he indeed showed that you need either something like h log x or h to the omega 1 in order to learn parities. Okay, so you just cannot improve over those two basic algorithms.
So in general, what is x? Sorry, so x is...
X is the examples. H is the hypothesis.
So in this case, H is like possible parities, and X is what?
X is like the 0, 1 to the n, because you get various x's and you get... Yeah. Okay. And So his work was really tailored to parities. It really, really used the fact that we were talking about parities. It asked, okay, so if you learn parities, it makes sense to look at affine learners, like learners that only do linear stuff. And then for these sort of learners, he was able to prove a very strong lower bound just by all kinds of linear algebra and things like that. And then he showed that basically any learner might as well be linear. Okay, so he really settled this problem for parities. Then he had another work with Gilad Kol and Avishai Tal, and they considered also smaller parities. Okay, so for example, the main case that they were interested in is parities where you only choose log n out of the n variables for your parity. Now, why did they care about this case? Because general parities is a very special class of hypothesis. Parities on very few variables are actually, it's like such a small and like innocent class. They just actually contained in other classes that people care about, like DNFs or things like this, juntas on logarithmic number of variables and so on. So this allowed them to get some results for some classes, hypothesis classes, other than just full parity. Okay, and they show that you need either superlinear space or super polynomially many examples in N. Okay. But this still doesn't resolve kind of the big question, which is what about general hypothesis class? Can you prove lower bounds on learnability with bounded space? And in fact, this was the question that Michal had in mind when she first heard this problem from Ohad. And what I want to tell you is about kind of our solution to this question. Okay. So I told you that it's going to be a connection between pseudorandomness and learning. So let me introduce the one definition from pseudorandomness that will be necessary here. I want to consider a bipartite graph that corresponds to my hypothesis class. So I have all the hypotheses on one side, and I have all the labeled examples on the other side. They don't have to be the same size. They might be. Notice that I'm talking about labeled examples. So example appears here with either 0 or 1. That is its possible label for it. And I connect one hypothesis with one example, one labeled example, if the hypothesis is consistent with this labeled example. So if I get like x and b, then if age of x equals b, then I'm going to connect age of xb. So this is, for me, the bipartite graph that represents this hypothesis class. And then I can ask about its pseudo-random properties, just the usual way. So I'm going to define capital D mixing if for every set of hypotheses, every set of labeled examples, I have mixing. The number of edges I expect is what it would be in a random graph with the same density up to kind of the standard error. Okay, and then kind of D gives you what's the multiplier of this like standard deviation kind of thing. Okay, so what I want to do is consider hypothesis classes that are mixing. For example, random hypothesis classes are going to be mixing. They are not captured by parities, even by small parities. So most classes are not captured by parities, but would be captured by this. By the way, this is what we know about parities. They are square root h mixing. Okay. So main theorem says any hypothesis class that is mixing has a lower bound. If you take the space bound to be the bound of the number of memory states to be sufficient, then you're going to need many examples. Okay. So here is the theorem, at least kind of simplified. We can get slightly better parameters. So suppose that the hypothesis class is order square root x mixing. We can actually, so it includes parities. We can actually go above parities, and we can even go above this order square root x. For now, let's say it's order square root x. Then you need either some number of memory states or h to the omega 1 examples in order to learn. And the thing to notice is that this bound that we have on the memory, on the number of memory states, right? So this, right, for parities, this used to be h to the log x. H to the log x is actually not true for such general classes, but probably something better than 1.25. The issue with this 1.25 is that this is superlinear in H. Okay, so it's right. So it was a challenge to get a superlinear number of memory states. We hope that we'll be able to improve this, but we don't know yet.
What's your conjecture? How far can you improve it? You're saying log x is...
I don't want to commit to a conjecture. No, but in particular, also the small parities from this Kol Raz et al. Is also mixing. And they actually have an example where you can do slightly better than h log x. Okay, so from now on, I'm going to denote the number of memory states, my low bound, the bound I have on the memory states is b, and I'm not going to mention again what this b is. But the point is that the number of examples we prove, this is really the right thing. We really show that you need essentially h examples, which is like what we had for parities in order to learn anything when you have this bound on the memory.
So for parity on log n bits, are they mixing? I guess they're not as mixing, right? So your theorem would...
No, they are as mixing.
Oh, even on log n bits, they are square root of 2 to the n?
Yeah. Because it's a subgraph of... Right, this is the thing about mixing. It's a very robust definition.
But then if you apply your bound and their bound, I'm just trying to see how do they compare for pairs?
So they have something much better. They have super constant here.
Oh, super constant, but not log x.
But not h to the log x. H to the log x is not true. Okay. So this is the main theorem.
And if you take a random hypothesis class like non-constructive,
this is the best. So we're talking about proving low bounds for random hypothesis class. So this is actually an interesting point. Usually we're used from circuits that looking at random functions, it's very easy to find low bounds, right? Because it's counting arguments and this and that. For learning, counting arguments don't work. Dealing with random classes is really hard. It wasn't known until this work.
So the bound you get for random is worse than the bound you get for parities, that the random has for parities in particular.
In what sense? No, but here we're trying to capture everything, right? It also depends on how mixing, right, you're considering and what are the parameters, right? It depends on, right? So it's not really a fair comparison. Okay. Okay, good. Let me argue, my favorite thing about this work is the framework, is the fact that we have this combinatorial way to think about, to prove lower bounds for space-bounded learning. And we introduce concepts that I think are really important for this study. So to me, this is the main contribution of this work. We give this pseudorandomness sufficient condition, this connection between pseudorandomness and unlearnability with bounded space. It's also nice that we have this, just a combinatorial sufficient condition for when something is going to be hard. And so the applications, as I said, for most classes, for random classes, we get lower bounds. And for classes that are error-correcting codes, in the sense that every two hypotheses disagree on many examples, these are mixing classes, and we get results for them. Okay. So this is the theorem.
So, and you get a lower bound, say, like for any pairwise independent.
Yeah, we can get. Yeah. We know many things that are mixing, and for all of them, we get a lower bound. Okay. Yeah. So we wrote this down, and then we put it on the ECCC, and we sent an email to the people who worked on those things to tell them, hey, we have this new general result. And one of them was Ran Raz, and a few days later, he writes to us that he too can get such a result, or at least a related result. So he eventually finished writing his thing, and it's now also on the ECCC. And this is what he proves. He considers an algebraic notion of mixing. Considers the largest singular eigenvalue of this matrix that is very similar to the graph that we consider. So he has this condition about the singular value, and then he gets very strong results that actually generalize his previous work on parities. The works are completely different, right? We're all about let's understand the concept and the framework, and let's be all combinatorial and nice, and this is all algebra. So I think that there is what to gain from both works.
Does this imply mixing?
What?
Does this imply mixing?
I think that it should imply mixing, yes. But the other way is not so obvious, right? Combinatorial mixing is a.
There's some converts for.
There are some, but they are not so smooth, right? It's a stronger thing in general to have this combinatorial mixing.
It's a billion lineal should have converts for graphs.
Yeah. No, and this is also about graphs, and you can probably also do them, but the converse, the parameters are not so good in this bilinear.
Works for random?
Yeah.
So it's better for random.
For random age, it does give better parameters. Kind of, the hope is that, the way we look at it, we wanted kind of this framework to be known, and the belief is that we should be able to also get the right quantitative bounds. It's just more subtle than you would initially think.
So this doesn't give the result for sparse parity? It doesn't apply there?
No, it doesn't. You can actually substitute and
It
see.
gives only log square and log.
Yeah, it's substantially weaker than for sparse parities, yes.
But for general parities, it matches his.
For general parities, it matches, yes.
But for sparse, it doesn't.
Yeah. Okay. More questions? Yes.
It's log h or log x?
It's actually log h. Yeah. This is why it's not so strong for sparse parities. Fewer hypotheses.
If this for log x, you get sparse parities too, right?
What?
If this h to the equals.
No, it's just not true.
It's not true.
With log x. Okay. Okay. So I wanna tell you about our work. Okay, I said it's a nice combinatorial kind of framework for thinking about lower bounds. And the first thing I need to do is kind of to model what a learner is. So let's do that. So suppose that we pick some hypothesis. This is going to be our underlying hypothesis H. And then we're going to have a bunch of memory states, up to B memory states. And we start with some arbitrary memory state on the first layer. And each time we're going to get some labeled example chosen at random, and we're going to switch to a new memory state that corresponds to the next time. Okay. And in general, we have this transition graph that tells us for every memory state, for every example we get, well, what's the new memory state. And the whole thing is that the number of memory states is bounded. And so on and so on. So we actually have all those many layers. And in the end, every memory state is associated with an hypothesis. And the hypothesis is what we output if we reach this memory state. You know, this is, oh, I think that H3 is the right hypothesis if I got here. Okay? And what's going to happen is that we're going to have a path for every sequence of random examples that we get. It induces a path in this graph that eventually results with a memory state that says some hypothesis. Okay? So this is a learner.
The degree is x here, the degree of
Yes.
everyone.
Yes.
So we're thinking it's like a deterministic learner?
So it's a deterministic learner because, yeah, the example. Yeah. Yeah, okay. Okay.
Can I sort of ask one more question before we go?
Yeah.
What is the error that right, you're showing it cannot learn this kind of function, so but is it totally uncorrelated?
So
or?
let's see.
Okay.
Okay, so here is the first concept that we want to introduce to study those lower bounds, and this is the concept of certainty. So what we're going to do, right, it's a lower bound. The learner is supposed to work for every hypothesis. We're going to pick, right, just like in probabilistic method, we're going to pick the hypothesis at random. Okay, so later we'll see that we're going to tweak with that and not quite pick it at random, but kind of disallow a few hypotheses and so on and so on. But initially, you know, let's just pick it completely uniformly at random. And now, for every memory state at every time t, we can ask how certain this memory state is in the identity of the underlying hypothesis. Okay. So we consider all possible hypotheses, and for each one we ask what's the probability that the right answer is age conditioned on we reached this memory state. Then we take squares, which means, so if we're absolutely sure, so there is going to be just one thing that is 1, then the certainty is 1. If we're really not sure, if we're like, it could be anything, I basically still have the uniform distribution over h, then I'm going to have sum over h of 1 over h squared. Okay, so I'll have only 1 over h. Okay? So this is the definition of certainty, and we also look at the definition on average certainty over all possible memory states at a certain time. Okay. And here is what we say. Initially, we're just going to pick the hypothesis uniformly at random, and the certainty is going to be 1 over h. You know, we don't know anything. We didn't learn anything. But then what can happen is that, you know, we see examples, and we update. We get more and more information, and we update our knowledge, and then maybe the certainty goes up. Okay, so this is the hope for a learning algorithm, that in the beginning it didn't know anything, in the end it knows. So in the end, we want the certainty to be, say, at least omega 1, right? If we have constant error, for example. Okay, so somehow the certainty had to go from almost nothing to really large. And the question is whether it can actually do that. So what we're going to show is that any learner that has this bound on the number of memory states at any time t, then we need to tweak things a little, but then the certainty doesn't go up by much. The certainty is essentially what it was before, times something that is about 1. Okay, so a priori, I see an example. An example gives me 1 bit of information because we're talking about like 0, 1 labeled examples. So supposedly maybe the certainty increased by 2, by factor 2 each time. And we say no, it increases because of the bound on the memory, it only increases by about 1. Okay? And you can see from here that to get to order 1, well, we need to run for h to the omega 1 steps. So this is what we get. Okay, and then of course you can change that, right? If you want different certainty, then you get slightly different things here. But, okay.
What is B here? As long as B is less than...
B is whatever we defined before. I told you
sorry.
B is like the number of memory states. This is the width there. We prove something specific for it. Okay, so this is our first contribution, this idea of certainty. And the fact that certainty may not go up unless you see a huge number of examples. Okay. This is kind of the proof outline. But I want to kind of go a bit deeper and highlight all the important components and the other concepts that we introduce. Okay, so the first question you may have in your mind is, what's the pseudorandomness connection? Why mixing? What's going on? So this is what I'll try to answer now. And I'm going to demonstrate in the case of, in like a very special case that we call heavy steps. What's a heavy step? This is a situation where you started with a memory at time t, and there was a very large set of labeled examples that all led to the same memory state at time t plus 1. Okay. Now, this is a situation that may occur in algorithms. In particular, the brute force learner has heavy steps because what's a memory state is like, I conjecture that the hypothesis is something. So every example that is consistent with this hypothesis, huge number of examples, is leading to the same memory state that says yes, we still think that we're consistent with this something. Okay? And every other thing leads to a memory state that says my conjecture is the next hypothesis. Okay. So heavy steps may be really useful. Right? So this is this example. I may go to all the examples consistent with some hypothesis H. Okay. Now, what I claim is that for heavy steps, it's really clear why mixing is helpful, why mixing implies lower bounds. So what's the situation? The situation, suppose that the certainty here is high, right? Because all we want to show is that the certainty doesn't, right, it stays high all the time. Sorry.
I mean low.
It stays low, sorry. So what's high is the number of possible hypotheses, okay? So a memory state has many possible hypotheses that are consistent with us being there. And now it gets one of many examples. So we have a very large set of hypotheses, or maybe in general a distribution on hypotheses. And then we know that we got one of like a very large set of examples. Okay. And mixing exactly ensures us that we didn't really gain much information, because the number of edges in between is kind of the same no matter what. We just, right, this is mixing. We didn't gain much information if all we know that the example is one of many possibilities. Okay. Okay. So this is the. Any questions? Okay. So this is the first case. In this case of like many possible hypotheses, many possible examples, because of the mixing, the certainty doesn't go up. Okay.
I'm a little confused.
Mm-hmm.
So, isn't it a deterministic? How can you have a large set of labeled examples? Are you talking about consecutive time steps or?
Yeah, t and t plus 1.
So, don't you request a sample? When you say you get a sample, are these?
This is so I'm
randomly
talking about the
generated?
transition graph.
They're randomly generated.
Yeah.
Oh, every time step you get a random sample. Not
Yes, and I'm talking
Okay,
here about the
request.
transition graph, not about
Okay.
what
sorry.
happens in some
Now I
execution.
understand.
Okay.
Alright.
Okay. Good. Okay. So this case is an easy case, but then of course this worked nicely only when there were many possible examples. So we didn't know which example led us to here. And the issue is that maybe transitions are such that there is maybe only one example that leads here. In particular, what we do is we save the current example that we got in memory. It means that we go to this new memory that completely tells us what this example was. Right, so this is this situation. And the question is, what do we do in this situation? Because here mixing doesn't help us. Okay, and this is the hard part. But here is the idea. The memory is bounded, right? So far we haven't used the fact that the memory is bounded. If the memory is bounded, you start with like B memory states, you end in B memory states, but every vertex, at every memory state, there are like X possible things that we may see. So on average, we expect each time t plus 1 memory to see something like X possible examples. Okay, so it's not, right, this algorithm that keeps remembering all the examples it sees, it keeps kind of expanding over and over, and right, there are never collisions. But if we have bounded space, we know that there must be collisions. Okay. So this is how we use memory, the bounded memory. And here is the idea. Well, you know, the fact that we got this labeled example here, it may give us one bit of information, but you know what? But we're not sure from which memory we got, and this is what's supposed to confuse the algorithm. So this is kind of the intuition. Okay. Except that, as is, this is false. Because what can happen, suppose that you may have many possible memories all leading to here, but for each of them, the set of possible hypotheses that makes sense is the same. Okay, so this is the situation that is equivalent basically to have one memory with some subset of possible hypotheses, and now I get another bit of information. So obviously my certainty went up. So the idea is we need something more than that. What we need to say is that if I have many possible memory states and I look at what are the possible hypotheses that are consistent with them, I get things all over the place. I can't get the same set. Okay. And this brings us to maybe the second big concept here, which is the concept of a knowledge graph and K expansion, K for knowledge. So what's a knowledge graph? It is a graph that summarizes what we know at certain time step. Like we may be in each one of those memories. Those are the time t memories. And we may have each one of those hypotheses. And we connect a memory to all the hypotheses that could be that are consistent with it. Okay, like so every edge here corresponds to there is a way, if this is the right hypothesis, to get to this memory state. Okay. So this kind of represents exactly what kind of all the information we have about the hypothesis, the memory states, and how they correspond to hypothesis at a certain time. Okay. And we're going to define some notion of expansion for this graph. It's kind of, usually when we talk about expansion, we talk about regular graphs. This graph is just, whatever comes from the algorithm, so it can be highly irregular. So you need to be very careful about your pseudorandomness definitions, but we do that. And then we want to say K expansion would be that like sufficiently large sets or distributions with enough entropy here correspond to many possible, like basically the uniform distribution, or nearly the uniform distribution of a hypothesis. Okay, and if this is the case, what we can say, if we have like a large subset of memories, there are many, right? Well, basically uniform over the hypothesis, and here we only get one bit of information on something uniform. Overall, we don't have much information here. Okay. Okay. Any questions about this kind of? Now, the main thing is that we need to show that K expansion is preserved, that K expansion exists in the beginning and it continues to exist at every time step, because we really need it at every time step. And this is what we do. And the interesting thing is that we need the certainty to be low in order to get K expansion. So we have this argument that says, well, if you have low certainty and good K expansion, then you will continue to have low certainty. But also, if you have a good K expansion and low certainty, you'll continue to have K expansion, and this way we can, continue throughout all the many iterations. Okay, and so this is roughly the argument for why K expansion is preserved. We start, right? So suppose that this is my new knowledge graph between time t plus 1 memories and the hypothesis, and time t plus 1 memories came from time t memories via our transition graphs. And what we want to show is that if we start with the distribution with kind of enough entropy here, then we end up being nearly uniform here. And here is what we do. We say, well, if we have memories of high probability, of sufficiently high probability here, they must have come from memories with sufficient high probability here, and also the examples leading here had to have sufficiently high probability. Okay. So what we're going to do is to focus only on memories here that have low certainty. We assume that there is low certainty overall, so there should be many such memories. Each of them has many possible hypotheses. Now we're doing this transition. We know that there is a good probability to reach the green set. And so because of mixing, we know that we don't get a lot of information from this transition, from this example. And we can say we don't get too much information from here because we knew that we had K expansion before. Okay, so basically this is the argument. Of course, there are many details, and the overall thing is quite intricate. Okay. Okay, so this is what I wanted to say about the proof. Let me talk a bit about open problems. So one thing, we showed that mixing is a sufficient condition for unalienability. And one question is whether it's also essentially necessary. right, we have very strong lower bounds. Very strong lower bounds for mixing classes. Do those lower bounds, very strong lower bounds, only hold when the classes are mixing? Maybe, maybe not. And in general, what we would like to have is a full theory of learnability with bounded space. What we would want to have is, for every interesting hypothesis class, say, okay, the trade-off between time and memory is this. This is the diagram that gives it. So we made a lot of strides towards this by considering all kinds of special classes. Yeah, but we still don't cover everything. That's it. Okay. Any yeah.
We have plenty of time for plenty of questions.
So what is a new? Oh, sorry. What is a new? What is some new? I mean, non-parity. I mean, can you give some specific new examples where you get? Where your conditions.
Random classes.
Random
No one knew how to say anything about random classes before. Random classes would not contain parities. No reason for them to contain parities.
What about so one thing about RAS and author's work is this applications to bounded storage model, this applications to cryptography. I guess parity is actually good because they give efficient encryption scheme. Random would be bad, I guess, in this sense. Any other, I don't know, DNF, I'm not an expert on learning, but anything else that might lead to new candidate encryption schemes against the space bounded attackers?
So which hypothesis class would you like to see?
I don't know. Well, I guess. Parity is almost
that cannot compute parities.
I can.
AC0.
AC0, okay.
Yeah. So for AC0, we don't have the right. We know that we don't have the right quantitative results, and this could be a way to get the right quantitative results. For them, we of course need to improve our quantities for this to happen.
AC0 doesn't satisfy your condition. I forgot what it's called.
AC0 does satisfy.
Oh, it does satisfy.
Yeah, DNFs already they satisfy this. Yeah.
Just to understand the role of the distribution, I should think of this result as for any distribution. It's true on a distribution by distribution level for the learning with the random examples. Yes.
So, right, the learner's job is to deal with every distribution. So it's enough that we show some distribution, okay? But we actually consider very concrete distributions, which are essentially be uniform over all hypotheses. We later modify it somewhat. As time progresses, we may throw out hypotheses that we don't like, but we don't throw out too much.
For your first order problem, if you just took a graph that was mixing and you put one that wasn't, and you put them together, would that
No, but right, the question should not be understood in literally. It should be understood in, can you extract from every hypothesis class that has those strong bounds, can you extract something that is mixing? Okay.
Can you actually prove something like Pseudorandomness, like Andrei asks, if you see fewer than this number of examples, not only you cannot learn, but in fact, I don't know, the answer in some sense is pseudorandom. For encryption application.
Basically, this is what follows from what we do. We basically say, you don't see enough examples, and you have this bound on the memory, then you basically don't know among all these.
So the correlation bound you get is something like 1 over h raised to some constant power?
Yeah, which is really good if you have h.
Is it enough for privacy? As I said, for parity somehow it just says that if you don't see enough examples, ciphertext hides all information.
Maybe we should take other questions. And
yeah, I'd be happy to
to
think about specific applications.
Okay, well, let's think then again.